What's that? Oh. Okay. So we were looking at the map and you guys were saying dark green was where the highest populations are. So you were saying that the dark green is where all the highest population, and then I would like to know um, why you think that way.
So Ms. Ned, they said it's on the most populated countries.
So the dark green is on. Name one of the most populated countries that you see dark green on.
Someone said Russia, and then someone said they think that blue is the most highly populated.
Okay. So I feel like there might be a little bit of misconceptions that we have to address. Because if I was looking at all the dark green, I would look at the United States. And then if you look above the United States, that is Canada. But also above that is like no one lives there. Right? And then if you look at all the other dark green places, it looks like places in the desert or places that aren't very inhabitable. But Kelsey, yeah, if you look at the blue areas and even purple, what country is that purple?
India.
Absolutely right. And if we were to watch or if we were to review the people paradox, there was a lot of talk about the Indian population. So put some things in the chat that talks about the Indian population. because that is purple.
So India has one of the highest fertility rates.
Mm-hmm. Fertility meaning births, right? Birth per woman. So India has the highest fertility rate. We're going to go ahead and assume that the purple means the highest population density, right? Then we have blue. And then what? Do you think it's the light green or the medium green? And why?
So ladies, why are you saying light green? So Kelsey says because those countries are densely populated, but to an extent.
So we're looking at Mexico. Um, what is that? That's a little bit of Europe.
Mm-hmm. South Africa, Madagascar.
Mm-hmm. The coastal areas, kind of not inland of Africa. So that is right. Mexico has a higher population density than the United States. I mean, I have more people. I'm gonna have to check the census on that. But I know that there's a smaller space with more people in it. Does that make sense? So we're talking about the density. So if we're looking at characteristics, um, well, let's talk about the pandemic we're going through right now. They can probably predict where there's going to be more cases of the coronavirus by looking at the population density because it's passed from person to person. We're going to get into that limiting factor as well. So if we're looking at the map, population density is how many organisms are in a given area. Dispersion is how it's spread out. And so, if you're talking about Russia, someone mentioned that Russia may have a large population. If Russia had a very, very large population and a lot of space, then it wouldn't be considered heavily populated. Okay, and then on Tuesday of next week, we're going to do some math problems about population growth. So that's just something for you to have a little later. But the growth rate formula is birth plus immigration minus death plus immigration. divided by the total population is going to determine how fast a population will grow. Birth and immigration add to the population. Death and immigration take away from the population. So if you look at the words below, immigration is moving into an area and immigration is leaving an area. Okay. So that's some characteristics of a population. We're going to look at, okay. So if we were doing notes with four corners like we've done in class before, I'm going to let you guys decide what we want to talk about next. So actually, the only other two things we'll talk about is the 10% rule and factors that limit population growth or population size. So put in the chat. First one to comment in the chat about which one they want to talk about first wins.
So 10% rule or factors that limit population size? Kelsey said 10% rule.
Kelsey wins. Okay, this will be really quick because I know that we talked about this when we were doing lion, tigers, and bears, and we had to look at some food webs and some ecosystems. So this is just a kind of overview just to make sure that you heard it from us. So the energy pyramid, the 10% rule says that as energy moves through a food chain, it decreases and only 10% goes to the next trophic level. So the trophic levels that I'm talking about are autotrophs and heterotrophs. And within them, you have producers, primary consumers, secondary consumers, tertiary consumers. So if we look at this pyramid, there's an arrow that says the energy is lost. And if you look at the numbers, 100% of the energy is available at the producer's level. Where does that energy come from? The question is, where does the energy come from that is available to, huh?
Kelsey said the sun.
Okay, yes, from the sun. And plants take that in. That's why they're autotrophs. And they're producers. So they take in all that energy and they just hold it in their bodies in the form of carbon, which is the chemical energy. Okay, then along came something. What would be available at the next level? What's an herbivore? Put it in the comments. What is an herbivore? Give me an example. An herbivore. Okay. Deer?
Okay. An animal that only eats plants.
Very good.
Good.
So an animal that only eats plants has to be in that next level because the thing below it is just plants. So herbivores would only be available at that primary consumer level, right? So they're going to eat the producers and only 10% from that first level goes to the next. So that's why it says 100% energy on the bottom trophic level, and then 10% of the energy is at the primary consumer level. All right. So next example, it says secondary consumer. It could be a carnivore or an omnivore. So if you give me an example of a carnivore and an omnivore, will be great.
So Lizavius, is that a carnivore or an omnivore? Kelsey said humans are omnivores. Evelyn said
Tiger.
Evelyn, are those carnivores or omnivores? Okay, so Lizavia said alligators are carnivores.
Yes.
And Kelsey, a carnivore is a leopard.
So omnivores besides humans, because it gets a little sketchy when we start adding humans into food chains. We always want to be on top, but not in nature.
So can we get some omnivore examples?
Yes, Anthony.
Mm-hmm.
Some bears are omnivores. Very few of them are carnivores, but they are. Very good. Good bump, Kelsey. So let's say we have some carnivores on the secondary consumer level. Those would be smaller ones, right? Because something eats them. So it's not an apex predator that's going to be a secondary consumer. It's going to be a smaller carnivore if carnivores at all. So any of those, you guys didn't name any small carnivores. A bird could be a small carnivore if it only eats worms. So only 1% of that energy through meat eaters, only 1% of the energy can get to a meat eater because it's eating meat that's already only received 10% of that energy. So only 1% of the energy goes to the secondary consumers, okay? And then that top carnivore, the apex carnivore, is an organism that's not really eaten by anything except for maybe decomposers when it dies. So 0.1% of the energy gets to the tertiary consumers. And so when we look at this, we're not only looking at the energy and how it decreases, but also the number of organisms are going to decrease as it goes towards the top of the food chain. Any ecosystem that has an overload of apex predators is not going to be successful. Why? And I see you guys' comments. Good, Evelyn. Raccoons, possums, badgers. Yes. And so the question is, why is an ecosystem with an overload of apex predators not successful?
So Kelsey said they will soon die off due to competition for surviving rations to keep them alive.
Absolutely. There's competition there. So they'll eventually kill each other off. And which is when we looked at the lion, tiger, and bear, one of those reasons that they weren't all living in nature was because they would compete and outcompete each other. And that would not be good for the population beneath them. Okay, so that is the major part of the 10% rule. 10% of the energy available will go to the next level. But how or why is it only 10%? Where does the rest go? Well, this bullet right here says heat is lost through respiration in the everyday life of the organism. So while producers are sessile, meaning they don't move, they don't walk, they don't run around, they're going to be able to retain a lot of that energy. But the next level of primary consumer have to move, they have to breathe, and they have everyday life. And so they're releasing energy and living their life. And that's why only 10% is going to be passed to the next level. So if 90 is lost, 10% stays and it moves on. So it's only 10% of what was available, not 10% overall distributed. Okay. Are there any questions? If there are about the 10% rule, go ahead and put it in the chat. Also, my students have a flip grid. When I'm checking for your understanding, you can watch the video and then make a comment about if you need more description. But this is more description than that video. Okay. What was the other topic?
Factors that limit population size.
Factors that limit population size. Okay, great. There. Okay. So if you guys want to take a picture, or you can write it out right now, it's not, such a big deal. But we are going to go through these things and ask a few questions, and then after that, you'll be free to fly. So, carrying capacity is a factor that's going to limit population size. So, the carrying capacity is how many organisms an area can hold in a given space. So, if you think about carrying capacity of an elevator, and I give this example in class, I think I gave it already, but an elevator, it can hold 200 pounds, let's say, or 500 pounds. So what happens when the elevator has reached its carrying capacity? What happens when an elevator reaches its carrying capacity?
Someone said it falls, or it won't budge, or it will malfunction.
Yes, it's gonna get stuck. I'm always that person who does not want to be the last one on the elevator, because I'm like, what if the buzzer goes off and it doesn't work? So that's a perfect example of, we can compare it to an ecosystem where there's a huge population of something. At some point, that population will not be able to grow anymore. And that is where it's gone beyond its carrying capacity. So if on the elevator, it's going to go up, down, up, down, up, down for 450 pounds, but that last 50 pounds, either that person's going to have to get off or the elevator is going to get stuck, right? Latavius? Okay. So that's what a carrying capacity is. And when we look at populations, Anthony. When we look at populations, they are kept in check based on this carrying capacity theory, where a given area can support that population. So I want you guys to put in the chat, what are the things that a given area needs to support a population? What are the things that are needed in that area to support a population?
So food.
Mm-hmm.
It was sent to me privately. um,
Potable water. Yes,
Potable water.
Kelsey.
Yes, trees, oxygen, food source, water.
Yes. Very good. And so that leads us into the very next topic, which is limiting factors. So without these limiting factors, a population can grow, 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 grow. No, with these limiting factors, the population can grow, but there's only so much. So what you mentioned, water, that definitely is something. Oxygen, yes. A food source. Also, if it's an aquatic ecosystem, it's about salinity. So how much salt in the water, if it's marine or if it's fresh. The available sunlight to trees. So I don't want us to only think about animals. We want to think about all living things, which includes bacteria. Um, it includes trees, grass, insects, snakes. So all those things are going to need these things to live. So what limits the growth is the availability of all of these things. So let's take aquatic plants, for example. What do aquatic plants, what do water plants need? Keyword, plants. They need sunlight. Yes, Kelsey. What else?
Me privately, water.
Yeah, they need water. We did that soil test. Some bacteria. Bacteria in the soil, yeah, they'll help. You guys, we did the soil test where you guys tested 4 different colors on the top of the test. Then you had to read it. What were you testing for?
Okay. Nitrogen, potassium, phosphorus.
Yes, nutrients and pH. That was the last one.
Mm-hmm.
Good. So, plants, aquatic plants, would need nitrogen, phosphorus, potassium. They don't need water because they live in the water. They will need sunlight. They'll need some oxygen. Very good, Brooke. So, which of those things would be a limiting factor to an aquatic plant? If you could pick one thing, what do you think it would be that would limit the population of an aquatic plant? My dog.
So we've got oxygen and pH, some people said.
Mm-hmm. Anyone else?
Anthony said sunlight.
Mm-hmm. Okay. So the actual, like if I were giving you a test, the answer would be phosphorus. And it's just because phosphorus doesn't make its way into water systems as easily as for some reason it's nitrogen and potassium. So phosphorus is a limiting factor for aquatic plants. So if you go to an area and you don't find a lot of plants in the water, it's probably because there's not an availability of phosphorus in that area. That's the truth. But you guys are also true with your answers as far as sunlight, because we talked about eutrophication, where the plants, the aquatic plants are blocked and then they don't get any sunlight. And then indirectly, they don't get any oxygen either, because the fish can't give, wait, no, what can't give off? No, the plants can't give off oxygen to the fish. But remember, plants don't need oxygen. They take in carbon dioxide, and they get that from fish. Okay, so that being said, there's specific things in every population that's going to limit the growth. For plants, yes, it probably is going to be sunlight, number one. For Ms. Bannerman, name another organism.
Plant or animal, doesn't matter.
No, it doesn't matter.
A rabbit.
Okay, so a rabbit's limiting factor could be what? Carrots. Yeah. Or like jelly beans, because they eat them? No. Just kidding.
Just teasing y'all.
So yeah, so carrots or grass or even water would be would be a limiting factor for rabbits. So you're not gonna walk through the desert. You might see a desert hare, but you're not gonna see Peter Rabbit. He's not gonna be excited about going through the desert, because they're gonna be looking for lush foraging, right?
Mm-hmm.
Okay. So I think we have an idea about what limiting factors are. Just give a thumbs up if you understand limiting factors. They stop the growth of that population. And most limiting factors are going to be abiotic. The only non-abiotic one would be like competition. So we're going to look at density dependent limiting factors, and then density independent limiting factors. And we'll be done. It won't take long. I see lots of thumbs ups. Very good.
Mm-hmm.
Very good. Okay. So density dependent limiting factors is basically what we're going through right now. So why would I say that stay home safe? Is that what this thing is called that we're doing? Shelter. Shelter.
Yes, we're going to stay home and be safe.
Shelter in place.
Yes.
Why is shelter in place considered density dependent limiting factors? So if you look at the definition, density dependent limiting factors are related to many organisms in a given area. So a density dependent limiting factor can be disease. It could be the result of crowding, which is stress. Also, hunger is a result of having too many organisms in a given area. So why would our shelter in place be considered the answer to a density dependent limiting factor? because the coronavirus, yes, Kelsey, Miss Rhoda, the
Yes.
coronavirus is a limiting factor to the human population right now. It will stop the growth of the human population, right? And it's because we're all in communication with each other. So we're talking and touching and coughing and laughing and hugging and partying and being close to each other. So we have this shelter in place, which removes everyone from being together, because the more we are together, the more coronavirus cases there'll be. So the coronavirus is a direct example of a density dependent limiting factor. So that's why they stopped all that and are making us stay at home. Because if we kept on with our lives the way that it was going, everyone, it would wipe out our whole human population. Okay. So a density independent limiting factor. Oh yes, West Nile virus is also a density dependent limiting factor. There's been tons. The common cold is as well, which is why we were wiping down our desks and separating from each other. HIV is a density dependent limiting factor. Why is hunger considered a density dependent limiting factor? Or better yet, why is food? Yeah, I see that. It says the production of food can catch up to the rapid grow can't catch up to the rapid growing human population. So the more people that we have, the less people can eat. So hunger is kind of a byproduct to having too many people because it can't feed them. So a density independent limiting factor happens in spite of the population that's present. So natural disasters, hurricanes, and earthquakes. Those are the ones I want you to really focus on, because a hurricane, if you remember Hurricane Katrina, it happened in New Orleans, but it could happen in Texas, or it did happen in Gulf of Mississippi. But the whole thing was about a natural disaster that hit land. It wasn't because there was a lot of people there and that's why the hurricane happened, right? In California, there are earthquakes all the time. It is not directly connected to how many people live there. That's why it's density independent and not density dependent. If coronavirus were a hurricane, we'd all be dead because it has nothing to do with sheltering in place. Okay, so those are the differences I want for you guys to understand when we're talking about population growth. There's a lot of different scenarios, but overall, you need to understand there's density dependent limiting factors that's mostly related to diseases or crowding, and then density independent limiting factors. So did you guys know that with density dependent limiting factors, it's not always within one population. Some of the issues can affect other organisms as well. So if we're talking about the coronavirus in humans, it is been detected in other animals as well. So a tiger in the Bronx Zoo probably never would have been exposed to corona if it were in nature. But because of the proximity of humans, then the animals that aren't human also are affected by it. So that is another nuance of density dependent limiting factors. Okay, are there any questions about factors that limit population size? Okay, thumbs up if you got it. So what we're gonna do is for the rest of the week, you guys are gonna be working through this food chain, food web kind of self-directed activity. And we'll post it. I'll post it today, and then you guys will have. I don't know. You guys will have Thursday if you need help with it, and then Tuesday is when we'll meet back here on a Zoom with the rest of the topics. So if there's no more questions, I think we're good. Ms. Bannerman, Ms. Hathorn?
We're all set.
All right. Yes, this will be recorded, but I appreciate you guys showing up. We're looking and seeing who all is being super active, and that is really important for us because we wouldn't be here if you weren't. All right. Bye.